right? So I lead a group where we want to enable a collaborative future where data, like energy generation, is sustainable and data informs decision, right? So data informs decision, I think, is something we share. And then we say also models are understood by everyone, right? So the team of like 7 PhD students, 2 postdocs, don't ask the math. It turns out to 8 posters. You can visit like down in the hallways during this conference. So let's kick off with the motivation, right? So I'm investigating energy systems because we have the Helmholtz AI group for energy here. And energy systems are getting increasingly more complex and require some transparency because they're getting so complicated, so that's really tough to understand them, right? So here I sketched the transmission system grid that spans from Portugal and Spain, where you might have heard there was an outage, all the way at the moment even to Ukraine and the Baltic grid, right? Those were synchronized last year and this year to the same grid, right? So this is like one large synchronous machine you could think of, because if one part fails, even other parts might fail, right? So in the Spanish blackout, parts of France also experienced the blackout because it is coupled, and then they cut off the connections to Spain so that the rest of continental Europe kind of could continue operation. And we need to balance supply and demand at all times, at all spatial scales as well. But I would also argue we really need explanations in such systems, right? So this is a critical system, critical infrastructure. And obviously, if we want to do a forecast, a prediction, or maybe a control suggestion to an operator, they need to understand and trust this, right? So ideally, this is provable, that this is stable, and so on. Typically, we don't get exactly there, but at least give some reasoning what the AI model is telling you. And also on the consumer level, if you personally want to adapt and your electric car is charged to 20% in the morning when you get in, ideally it would provide you with an explanation like, okay, during the night there were extremely high electricity prices, so you earned a lot of money by doing this, or maybe you get reimbursed in some other way or form, and then it tells you, okay, you only have a commute scheduled to your workplace, which is close by, so you only need like a low share of charge. Okay, so putting this into action, I just gave like 2 small examples which we pursued in our group, and again there are many more on the posters of my group. So one is anticipating extreme events, and this is the story that we posted a measurement device on the island of Mallorca, which is not only physically an island but also electrically it's an island, which means that it's not part of this huge synchronous area, but it has to balance its own supply and demand locally. It can rely on an HVDC link, so high voltage directed current, towards the Spanish mainland. And what we see there is, like on the left-hand side, some interesting statistics in terms of the frequency as we observe it, right? So you see some huge peaks there, and this is typically when control via the link kicks in. So the deviations are too large, the system might get unstable, so now they say, okay, please, mainland Spain, give us some power, or we export some power over there, so we keep our system balanced. Right? So we see this here, right? So if the frequency deviation is too much, we see on the lower curve that this HVDC import then kicks in and keeps the system balanced. And now the question we asked was, can we explain and understand when and how this activates? Right? So first thing we did is just like a data analysis, right? So we looked at the number of events, when did it deviate to a high or to a low value. And we saw already some seasonal patterns here, right? So you can see in the middle of the years, we have this peak. So it tends to be that we have more events in summer. Okay, why do we have more events in summer? Because it's a holiday destination, right? So people go there on vacation. Air conditioning in the hotels actually consumes a lot of electricity, which means then you have higher need for electricity, right? So that kind of makes sense. And actually, we also see that many of these events are quite short, right? So in many cases, you do see a large deviation, but then at some point control kicks in, and then everything is stable again. And so even down to the like second level, right? So many events are like just few minutes to like several seconds long. Okay, so then what we did in terms of working towards anticipating this was something we called like a decision support tool, right? So the idea is sketched out here, that we built a machine learning model. In this case, because we're mostly working with tabular data, so tables, we went for trees. I mean, I will show you an example in the next slides where we deviated from trees, but trees perform extremely well on tabular data. And the idea was you get a prediction that tells you, okay, soon you will use like the HVDC link, so you will need to import power. Right? And one idea of why we want to do this is that you could then inform operators before they need to do that maybe some manual action might be necessary at some point if you don't want to automate the whole system. Right? And ideally, you also give an explanation. You don't only say, okay, alert, you will likely need power, but it will tell you, okay, because of these and these reasons, we think you will need power. Right? Okay, so how does the model work? Overall, the performance wasn't that great, you could say, right? So in the different categories, in particular of the no event, the middle row, it works fine, right? Because the no event, we had like the most support in our data set, right? So most data points in our data set were no event, nothing happened. And for the deviations in either the low or the high extreme, we had only few measurements, so the support was not so great, so the training was also not great. So the question then is it useful to have such a tool? And one interesting observation was that actually many of these false alarms, right? So you tell there's going to be an event, but there's no event. Most of these false alarms are actually then later on followed up by an actual event, right? So the only thing that was wrong was kind of the timing. So we already, like the algorithm already thought, okay, there's going to happen something, and maybe it didn't happen in the next 15-minute interval, but maybe in the 10 minutes after that, right? So we only missed it by like one window in the processing scheme there. So I think this is actually still fine, right? So you can see like some events are maybe an hour later, but several events are just like within 1 hour of our prediction. Okay, and then I told you we want to make this transparent, right? So what we used here was so-called Shapley values and Chap as an interpretation tool. I think maybe several of you are already aware of this, so I didn't introduce them here. Talk to me later if you're interested. And what we see is mostly it relies on like the frequency deviation and stuff like this, so mostly autoregressive features, because we didn't have that rich feature sets to include. We included something like low generation, calendar features, stuff like this, but likely we are missing some interesting information about, I don't know, maybe the pattern of the tourists on the island or specific weather information, right? If we feed this in, maybe we can get more specific domain interesting explanations. But what I think is quite critical here, again, is if you don't want to just rely on linear, simple models, here we do see that the machine learning model actually learns nonlinearities, like saturates at some point, and so on, right? So if you do see this non-monotonous, non-linear behavior that is learned in the model, this justifies that you do need maybe a data-driven, more complex approach than something simple linear. Okay, so very quickly, putting a spotlight on another approach was modeling uncertainty, right? So again, we looked at the frequency. We again built a tabular data set with like frequency and calendar and generation features. We trained machine learning models, trees, and this times also MLPs, for example, just as baseline neural networks. But the difference now was that we didn't only predict like the mean, but also the standard deviation. And then the interesting part we asked, or interesting question I think we asked was, what is the feature that is most relevant for the mean prediction, but what are the features that are most relevant for the uncertainty, right? So is it the same, or will it actually use different features to explain whether it's uncertain or not? And from a methodological point of view, we used this TAPNet as a neural network approach that was designed for tabular data. We extended it to something we called ProbaTAPNet, a probabilistic TAPNet, where we predict both the mean and the standard deviation. And we do get like R2 scores in the deterministic case that are comparable with a performance there of like previous tree-based models and the daily profile as a benchmark model. I didn't include the CRPS scores here we use for the probabilistic, sorry for that. And then we also looked into, again, explanations, right? So this is kind of the part that was then interesting, right? So again, we used SHAP, we computed the most relevant features, and what was quite interesting for us is that ideally we want to build something that is true to the data, right? That would be the best approach, so that you understand this is the system, these factors actually influence your stability or influence the uncertainty of your stability, etc. And what we mostly get is something that is true to the model, right? So we get a model that performs well, and hopefully we explain at least the model, and not necessarily exactly what the data is yielding in this process. But what we see here is, so we have the sum of other features, kind of the most important, but below that you can see, okay, load generation features like certain RAMs, like gas, hydro, and so on are important. But what is really interesting is that the ranking, which is the most important feature, differs between the different models, right? So the models can't really settle on this is the most important feature or that is the most important feature. And this is for like one approach. And this is now, so this one was for XGB and TabNet, meaning deterministic approach. This is for the probabilistic approach. And we see, again, they differ quite a bit, right? So even the uncertainty explanation, right? So how much it varies, again, this is not necessarily the same. So here we see something like other generation and bio cluster is like quite high, and here it doesn't really appear in the first features, right? So the models use different features based on the model structure, and they use different features to explain the mean and the uncertainty prediction. Okay, so to sum up, right? So I pitched this idea of like a decision support tool we used for like extreme events, how I called it, like large deviations in the balance of an islanded power system. Then we also investigated like tabular data with something we call probatabnet, but also you can do it with tree-based approaches, you prefer those. And we use overall like explainable AI to understand and operate systems better. Okay, here I listed the posters of everyone involved in the work, and like my PhD students who are also assisting with these sessions and timekeeping. Thank you.
Any questions to Benjamin? If you have questions, just go to one of the microphones at the aisles.
Hi, thank you for the presentation. I have a question just to make sure I clearly understood. Are you considering your problem as a time series anomaly detection problem?
Yeah, this is a great point. So what we do is, so we use kind of a classification on something like we extracted as more or less tabular data. So yes, we start with a time series. What we then do is we hack the time series into individual bits, and for each of those time frames we ask, is this time frame going to be like anomalous, like extreme or not?
And maybe a follow-up question, have you considered maybe taking, so instead of considering individual points, maybe, how to say, windows of fixed length?
Yeah, I think like in general, like we sometimes have the problem with different time resolutions, for example, that makes it quite tricky working with the window. So the frequency we have like with 1 second resolution, so we are already windowing this in a sense to then go to the 5-minute or 15-minute resolution we are working with on the generation data, for example, right? So we already have to match like different resolutions, but yeah, windows looking further into the past, I think that's a good idea. Yeah.
Thank you.
What time for one very quick question?
Very quick question. Okay, super quick. I find the Shapley values applied to uncertainty super interesting. Do you have any actual practical use cases where those explain something of the real world?
Okay. So first of all, Alexandra, can you please? So this is the poster you want to talk to. Thanks. Yeah, this is going to be the quick answer. So yes, just talk at the poster in the interest of time.
I am completely satisfied with the answer. Let's.
All right. Thank you again.